Our last topic in the circular motion unit are banked curve problems. Now, what a banked curve is, it's kind of a mix of a ramp and circular motion. And you see banked curves. It's an engineering staple of roadways. If you ever watched a NASCAR race and you look at the turns, those turns are very steeply sloped. That's a banked curve, as opposed to let's say like a track, like a running track, like we have outdoors at the high school, where the turns are not, they don't have a slope to them, they're flat. Okay, so we're going to see how banked curves actually help us to turn. Many curves on roads are banked. As a matter of fact, a lot of what I usually think of as examples are like exit ramps on the thruway or on at some highway. That's just a lower angled version of the banked curves that you would see on a NASCAR track. If you ride a roller coaster, a lot of times they'll bank the curves because it's easier on your body if you go around a banked curve, surprisingly, as opposed to going around a flat curve. Okay, so let's see why banked curves are so useful. A 3,000 kilogram car is making a circular turn of a radius 40 meters on a flat road surface at a speed of 20 meters per second. How much friction is needed to keep the car from slipping? So let's imagine that, and I'm going to skip some of the drawings I've done in the past. Let's imagine that I'm just looking at the behind view for a car that is turning to the right. So the car is turning to the right, so the center of the turn is off to the right. That's the C direction, and I'm going to call that the positive Y direction. We know that there's going to be a normal force upward from the road. We know that there's going to be a force of gravity downward. And we also know that there's going to be a force of friction, because otherwise the car wouldn't turn. The car would simply go straight through its turn and not be able to turn right, so friction must be pointing to the right. Friction in this case is the centripetal force, so it's equal to MAC. So it's equal to mv squared over r, and I can solve for how much friction is needed by plugging in my values. The mass is 3,000 kilograms. The speed of the car as it turns is 20 meters per second. We got to square that, divided by a radius of 40 meters. So we do 300 times 20 times 20 divided by 40. I get a force of friction of 30,000 newtons. Now, if this amount of frictional force is the maximum that could possibly be generated between the car's tires and the road surface, what is the coefficient of friction? That word maximum, again, is important. Remember, when you see that, it usually refers to something being the maximum force of static friction. Cars do not experience kinetic friction if they're functioning as is. The tires should not be skidding over the ground. We're talking about static friction here. The tires don't skid on the ground. They're not moving. The tire surface does not skid or move relative to the ground surface when it's in contact with it. Therefore, we're talking about static friction. So we're looking for the coefficient of static friction. When we're looking for the maximum force of static friction, we know that we can use this equation, Ff equals mu Fn. And I already know what the force of friction is. I can find the normal force by simply figuring out the normal force from my free body diagram from up here. Fn minus Fg equals may. The car is obviously not going to start accelerating up off the curve or down into the curve, so the acceleration is 0. Therefore, Fn equals mg, which means it's equal to 3,000 kilograms multiplied by 10 meters per second squared. So Fn is 30,000 newtons. Very similar to the force of friction, which is also coincidentally 30,000 newtons. So if you divide 30,000 newtons by 30,000 newtons, you get 1 for a coefficient of friction. Now, if you remember anything about coefficients of friction, they're usually between 0 and 1 and usually a little bit on the lower side. You can have high coefficients of friction, but it's very hard to do. So a coefficient of 1 between tires and the road surface is very hard to get. Think about how grippy those tires would be, almost to the point where it's probably going to shred the tires up a lot. It's very hard to get this to happen. Regular cars wouldn't be able to handle this. Okay, so if you're trying to go this fast around this type of curve, it's going to be very difficult. You would need very high coefficient of friction, and that's probably not going to work out very well in your favor. And just by the way, let's try and solve symbolically for mu, because we're going to compare it when we get the symbolic answer for a banked curve. Now, how are we going to do this? We know that let's see, we know that the force of friction ends up being equal to mu times Fn, which is mu mg. Force of friction equals mv squared over r equals mu mg. Cancel out my m's, divide both sides by v. I get that mu equals v squared over rg, telling us that if we go faster around a curve, we need a greater coefficient of friction. If we go around a tighter curve, we need a greater coefficient of friction. And if we reduce the force of, if we reduce the gravitational acceleration, the acceleration due to gravity, we would also need a greater mu. Because if you think about it, that would mean if you reduce g, your normal force is not going to be as big. So that's why g ends up being a factor there. We're going to remember this, and we're going to think about how this changes if we have a banked curve setup. So, let me just make sure that we have everything down here. Yes, okay. So now, we're going to imagine that the road surface is banked at a small angle of 5 degrees. Now how much friction is needed to keep the car from slipping? So here's what we have now. Here's the road surface right here that I'm drawing right now, and we're going to say that's about a 5 degree angle. It's really a lot more, but for this drawing, but let's say it's 5. And there's your car. Now the car, it's kind of tough to imagine this. The car is going into the page, let's say, and turning to the right. So if we had a depth, if this was a 3D image, you would see the car receding from you and also turning to the right. And this ramp, so it's kind of cutting across the ramp, but this angle remains consistent as the car goes like this, as the car turns to the right and goes into the page. Okay? So, what we're going to need to start off is a free body diagram. And this free body diagram is going to look sort of like one for a ramp, but it's also going to have some key differences. So we're going to label this as car. We're going to have an axis, and the first difference is our axis. You might remember with ramps, we used to tilt our axis. We are not tilting our axis this time. C is going to point straight to the right as the car turns to the right. Y is going to point up. The reason for this is on a regular ramp question, the car or the object moves either up or down the ramp. It accelerates either up or down the ramp. The motion is aligned with the ramp itself. In this case, we don't want the car to accelerate up or down the ramp. We want the car to accelerate purely towards the center of the circle. And if the car is not slipping up or down the ramp, then the center of the circle is exactly in the horizontal direction to the right. So our axis, it makes the most sense if we align our axis with the direction of acceleration like we normally do, for our axis to point exactly to the right. Now I'm going to add in the forces. Let's do the easy ones first. We know the force of gravity is going to act down. We know, since it's on a ramp, that the normal force is not going to be straight up, it's perpendicular to the ramp surface. So it's going to be almost straight up, but off at about a 5 degree angle. So there's Fn. And this next part is actually something that I just have been looking into recently. Imagine that this car was actually not moving at all. Okay, imagine it was stationary. The car would tend, without friction, to slip down the track. Okay, so if the car is not moving, then friction actually points up the ramp, like this. Okay, if the car is moving really fast, there's a tendency for this car to imagine it was moving so fast that it couldn't negotiate the turn and it started to slip up the ramp towards the outside of the turn. If there's a tendency for the car to slip up the ramp, then friction must point down, and that's what we're going to study primarily. Okay, there is actually a speed that this car can go at where there is no friction necessary, and the car maintains its position on the ramp without slipping up or down, no friction necessary. That's called the critical speed. Now what we're going to focus on is this car moving fast enough so that there is no critical speed issues here. So that the car, if there was no friction, would slip up the ramp. We're going to have friction directed down the ramp. Okay, so if the car has a tendency to slip up the ramp, okay, without friction, that means friction must try and point down the ramp. I encourage you to look up those other scenarios and understand why they might occur. But we're going to focus on the scenario where the car is moving fast enough to slip up the ramp, and therefore friction must point down the ramp. Okay, the car tends to slip to the outside of the curve, so friction points to the inside. You can see here that we're going to have to do some trig because our normal force and our force of friction do not align with our axis, and that's fine. Okay, you can see that the components should probably be approximately like this. Okay, here's the C component for FF, Here's the y component for ff, y component for fn, c component for fn. Now the issue is, how do we reconcile our angle theta of 5 degrees with which angles are 5 degrees? And it's kind of obvious here, but I'm going to go through it anyways. If you notice that our diagram, our free body diagram, has a shape that's kind of like this, that corresponds to a flat line extending and the ramp extending this way. And so this angle right here must be 5 degrees because we know that vertical angles are the same. So this angle right here between FF and its C component must be theta. And if this is theta, then the angle between FN and its C component must be 90 minus theta, which means that the component between the the angle between the Y component and FN must be theta. That is important for figuring out so that we know which trig functions go with which components. Remember that cosine is attached to the component that is adjacent to the force that's getting split into components. So this is so let's see here. We have a theta right here. The theta is adjacent to this component, so this must be Fn cosine of theta, which means this must be Fn sine theta. This component of FF is adjacent, so that must be FF cosine theta. This must be FF sine theta. Okay, now this is going to be a pretty long and involved mathematical working, but stay with me on this, okay? It's going to pay off in the end, and you have a homework question that is very, very similar to this. It's not an exact copy, but it's very, very similar. Okay, so I'm going to work with you on how to go through the algebra here. What we're going to do now, oh, and by the way, it says how much friction is needed to keep the car from slipping. That's not really the question I'm trying to ask here. I'm really trying to ask what is the smallest possible mu to allow the car to go around this curve in these conditions, okay? Before it was 1, now we're going to see if that changes at all. We're going to write out our net force equations. We're going to start in the y direction. We only have 3 forces in the y direction. F net y equals, in the positive y direction, Fn cosine theta. In the negative y direction, minus FF sine theta minus FG equals MAY. If this car is not accelerating up or down the ramp, then we can say that the AY is 0, and therefore we have Fn cosine theta. If this is the smallest possible mu, that means we have the largest possible force of friction before this thing starts to slip, so we can change this to mu Fn sine theta equals mg on the other side. Now, notice that I have an Fn on both these terms. I'm going to pull the Fn out, and I'm left with cosine theta minus mu sine theta equals mg. I'm going to divide that to the other side, and right now you're going to say, well, why did you just solve for mg? Or why did you just solve for Fn? It's because I know where this is going, okay? It's fine if you guys don't see where this is going yet. That's absolutely fine. This is the general process for doing this solve. So I have Fn equals mg over cosine theta minus mu sine theta. And you could plug this in, you could figure out what the normal force is, but there's no real point to doing that yet. Let's keep going symbolically. Now let's do the net force in the c direction, the centripetal force. That would be Fn sine theta plus, since it's also in the c direction, Ff cosine theta equals MAC, since we're talking about the centripetal direction. Well, let's see. Fn sine theta plus, we know that this is, again, the maximum force of friction, so we can change this to mu Fn cosine of theta equals m, and AC is really v squared over r. Let's pull the Fn's out again, so we have Fn sine theta plus mu cosine theta equals m v squared over r, and let's plug in our expression for Fn that we just found last time. We have mg over cosine theta minus mu sine theta times sine theta plus mu cosine theta over 1 equals m v squared over r. Now, The sines and the cosines, unfortunately, can't be canceled out, but something can be canceled out. We can cancel out this set of m's. We have an m on this side, an m on this side. We divide both sides by m. They go away. So, what I am left with at this point is the following. G, and I'm just going to put this in parentheses, sine theta plus mu cosine of theta over cosine of theta minus mu sine theta equals v squared over r. I'm trying to solve for mu. You notice I have a mu here and a mu here. Best thing for me to do would be to cross multiply, okay? And I'm going to cross multiply, and I'm going to take out this set of parentheses. So when I do that, I'm going to end up with gr sine theta plus mu gr cosine theta equals v squared cosine theta minus mu v squared sine theta. I'm trying to solve for mu. I want to get all the mu's on one side. So that means adding this term to the left side, getting this term over to the right. So that's gr sine theta minus gr sine theta plus mu v squared sine theta plus mu v squared sine theta. I'm actually going to pull the mu out on this side already, so it's going to be mu gr cosine theta plus v squared sine theta equals, let's see, v squared cosine theta minus gr sine theta. Divide this to the other side. Gr cos theta plus v squared sine theta. Gr cos theta plus v squared sine theta. And I get my final answer, make sure you guys can see this, of mu equals v squared cosine of theta minus gr sine theta all over gr cos theta plus v squared sine theta. And we're going to compare that to our answer from before with the flat trick. Mu equals v squared over gr. So, at first glance, what's going to happen to the top? V squared times cosine of theta. Cosine of theta has got to be between 1 and 0, so that's going to lessen this, and then we're subtracting something else from it, so the top's going to be smaller. The bottom, gr times cosine theta, that's going to shrink, plus v squared sine theta. That may or may not shrink depending on how much, but it looks like there's a good chance that mu is going to be smaller. And as a matter of fact, if I plug everything in from before, so let's see, that would be 20 meters per second squared times a cosine of 5 degrees minus 10 meters per second squared. R is 40 meters. Sine of 5 degrees. 10 meters per second squared. 40 meters. Cosine of 5 degrees. Plus 20 meters per second squared times the sine of 5 degrees. Now you have to be very careful plugging that all in. I'm going to write the answer up here, actually. Okay, so here's how we're going to do this. Let's see here. Okay, so 20 squared times cosine of 5, that's okay, that minus 10 times 40 times, okay, 360, 361. I'm just going to write that down. Okay, and the bottom, 10 times 40 times 5 cosine, 398, plus, let's see, 20 squared we already know is 400, 400 times 5 sine. Well, this is definitely not going to be equal to 1, so we do 363.615 divided by 433.340, and we get a mu of 0.839 approximately. we don't need as big of a coefficient. Okay, so what this actually means is it's easier to turn. You don't need as much friction. Now let's talk about why, very quickly, you don't need as much friction. Take a look at the free body diagram. Before, the only force causing the motion, the only force causing the turning motion was the force of friction. Now look what you have. You have only a component of the force of friction, albeit a very big component because cosine of theta is going to be very close to 1. You also have another component of another force. You have two forces helping you to turn this time. That means you don't need as much friction since another force is picking up some of the slack. The normal force is actually pushing this car around the curve. So a banked curve is easier to use. You don't need as much friction because the track itself, the ramp, the slope actually pushes you a little bit around that curve. It does some of that. It produces some of that force effort for you. That's why a banked curve is easier and is maybe not easier, but you don't need as much friction and it's a little bit less jolting. Okay, so that's banked curves. Like I said, the algebra is kind of a lot, but I just did the whole thing for you. I recommend if you are confused about something, go back and take another look at it. Okay, that's all that we have for circular motion. I'll be back when we talk about energy. I'll see you later.